One property of exponential functions. We know exponentials of functions are one-to-one. So for a greater than 0, we do positive values and not equal to 1, if a to the x sub 1 equals a to the x sub 2, the only way that happens because of the one-to-one function of it is if the two exponents, x1 and x2, are equal. And this can help us solve equations with exponential functions. We have this one to solve, 5 to the x. Well, let's think about 1 and 1/25. That's 1 over 3, 1 over 5 cubed, or 5 to the negative 3. So right now we're saying 5 to the x equals 5 to the negative 3. Oh, bases are the same. The exponents must be equal, and x equals negative 3. This one's a little different. The bases are different. What you need to do then, the bases are different. Wait a minute. 9 could be 3 squared. So this could be 3 squared raised to the x minus 6 power. And remember, when we have an exponent, a power raised to a power, we multiply the powers together. So this becomes 3 to the 2x minus 12, and we have 3 to the x plus 1. Now we have the same bases, different exponents. So they appear to be different exponents, but they must be equal. So x plus 1 equals 2x minus 12. Subtract an x from each side. X equals, add a 12 to each side, 13. And we have solved for our x. To solve these exponential equations, we want the same base. So 125 is 5 cubed, and then to the x power equals 5 to the first. Based on that, we have 3x equals 1, since the same base and the exponents would be equal, and x equals 1/3. Getting the same base here, well, 16 is 2 to the 4th. So 2 to the 3 minus y, bases are the same, so 3 minus y equals 4, negative y equals 1, y equals negative 1. Let's change this to 2. I'll make it 2 squared. And this, we could flip it and make it 2 to the negative x. So now bases are the same. Negative x equals 2, and x equals negative 2. 27 and 9, if we make them both 3, 3 cubed raised to the 4x equals 3 squared raised to the x plus 1. That would make it 3 to the 12x equals 3 to the 2x plus 2. So 12x equals 2x plus 2. 10x equals 2. And x equals 1/5. Well, let's do the bases. Here we have the exponents are the same and the bases are different. Since that's true, let's say the bases have to be the same. So 2 will equal x minus 1, and x equals 3, and x is greater than 1. So we're good there. We'll make this 2 squared raised to the x minus 1 equals, 2 to the 3x. So 2 to the 3x equals 2 to the 2x minus 2, or 3x equals 2x minus 2, x equals negative 2. We need to find the missing coordinate for each ordered pair. If x is 3, so we'll have this negative sign here, so it'll definitely be a negative. 3 minus 1, so we have 1/4 the quantity squared, or 1/16. Here we have negative 1/4 to the x minus 1 equals negative 4, which would be, multiplying each by negative, 1/4 to the x minus 1 equals 1/4 to the negative 1. X minus 1 equals negative 1, so x equals 0. We'll have a negative of 1/4 to the negative 1 minus 1, or negative of 1/4 to the negative 2, which should make a negative of 4 squared, or negative 16. Negative 1/16, so negative of 1/4 to the x minus 1 equals negative 1/16. That would be 1/4 the quantity squared equals negative of 1/4 to the x minus 1. So x minus 1 equals 2, and x equals 3. We can solve. The formula for compound interest, interest paid on both principal and interest, is an important application in exponential functions. Recall the formula for simple interest, I equals PRT, where P is the principal, the amount deposited, R the annual rate of interest expressed as a decimal, and T the time in years. That the principal earns interest. Suppose T equals 1 year, then at the end of 1 year the amount has grown to, the amount there equals principal plus the principal times the rate, that's the amount of interest, equals P times 1 plus R. That's the original interest, principal plus the interest. If the balance earns interest at the same interest rate for another year, the balance at the end of that year would be, here's the interest in the first year plus that amount times the rate for the second year, and factoring that we have P and an R, 1 plus R, and another 1 plus R. We factored it. Or P equals 1 plus R, the quantity squared. If we do this for a third year, this will continue to grow, and we'll end up with P equals 1 plus R cubed. Continue this way, produce the formula for interest compounded annually. So the amount you now have in the account equals the principal times 1 plus the rate raised to the T, raised to the number of years that it's been on deposit.